Warwick, and she's very passionate about open source. I believe, correct me if I'm wrong, Maha, this is a topic that has been with you since the PhD years, right?
Yeah,
And
masters even, but I don't want to go there. Yes.
okay,
Yeah.
so you've been doing this line of research for many years. Yeah, I mean, you've developed a strong expertise in this, and I certainly enjoy reading your papers. Very detailed work on how open source software developers work, and the implications that has for a number of different dimensions. And I guess this is one of the newest papers. This is not the 2016 paper, which I think put your name on the map.
I
But
wouldn't
this
go
is
that far.
right. This is a new one, and really looking forward to hearing about your research. I just want to also mention that um, the way we're going to structure the talk is um, Maha is going to present the paper. Then we're going to have a Q&A, and then for the last hour or so, whatever time is left, we will devote that time for questions from PhD students. I'm sure Maha has a lot of feedback and insights to share with us in relation to the publication process, but also in the research development, paper writing, collaborations with individuals like Emma Vast, who is also a star in the IS field, very influential researcher, also a female researcher, and I should say that.
Yes.
It's important because we have a lot of female PhD students, and I think it's important to showcase the successes of our female colleagues, because even though there are challenges, I think we should also, highlight the successes, and that there's light at the end of the tunnel.
Yeah.
I think that's important. So yeah, so I think all of those aspects, topics, issues will be discussed at the second part, in the second part of the seminar. But for now, we'll focus on the paper. So Maha, over to you.
Thank you, Panis. And again, I'd like to thank you publicly, you and then of course Tahir as well. Thank you very much for the invitation. It's a real pleasure, and it's a shame I can't actually be there physically with all of you, because it would have been nice to actually meet you. Because I'm going to have to make the screen a little smaller so that I can only look at my slides. That means I can't even see your faces, which is a really hard way to present sometimes, right? And communicate when you can't tell if somebody's irritated, confused, or actually enjoying your talk. I'm happy. I mean, I know we're going to have questions after, but if you have any questions, especially for clarification, I've tried to keep definitions and sort of things that I think might come up throughout the presentation quite clearly on the slide. But if there's anything that I've missed and you'd like some clarification, I may not see your hand up, but please just speak up, and I'd be happy to take those sorts of questions, or even more problematic questions if that's how Panis and Tahir like to actually organize it. I leave it to them.
Mhm.
I give you a little bit of background on this paper and then actually get straight into the actual presentation as well. So thank you again very much for the invitation. Just gonna, okay. So, all right. So to give very, very short history so that you understand that, yes, this is a paper that came out recently, but as we all know, and everybody in this room, online room probably understands, that doesn't mean that it's actually anywhere near recent a publication in the sense of writing. I mean, it's been some years in the writing. It was a number of rounds in revision at ISR, and it was not, I mean, I have to admit, it was probably one of the less straightforward papers to actually get published. I mean, I'm happy with the way it ended up and the way it looks, but it went through so many iterations that every single submission almost looked like a completely different contribution space. They started off as a paper for the special issue in ISR on humans, AI, algorithms, automation, augmentation. I can't remember the exact title. It was a bit of a mouthful. And so, I mean, that's where it started. And then it ended up going into the normal route for ISR because they didn't think it was enough of augmentation and automation. And I'll go through that later on, especially with the PhDs, to show them how we had to balance that going back and forth. And when they didn't want, the reviewers and the editorial board didn't want us to have the augmentation, and then when we took it all out, they wanted us to bring it back. So it's been one hell of a journey, let me just put it this way. All right, so this is a paper co-authored with Professor Emma Vast from McGill University. She is, as Panis already mentioned, and I'm sure all of you know her anyway, she is an amazing scholar, but also an amazing mentor to have. And for those of you, especially the juniors in the room, the early career scholars in the room, it's important to have somebody you can actually work with. That, I mean, and we all find different people, so it's not like one person is the right person for everyone. We find different ways of inspiring ourselves, getting ourselves to work, or having somebody who writes a lot. And most people don't hit all of those categories. To find the right co-author for yourself is going to be very determined by who you are as an individual as well. So sorry, that was just more for for the early career scholars. So this paper, it finally became titled as Algorithmic Interactions in Open Source. It is available online now in ISR, though I don't think it's got an actual publication like issue yet, as far as I remember. Okay, so make this work. There we go. So why did we do this paper? Putting aside the fact that this came from a special issue, motivation more based in literature itself. As Panis mentioned, I've been working on open source for a long time. Now, most people might get bored with any topic over so many years, but for me, I don't know. The problem is that open source sort of keeps giving me these curveballs every 3 to 5 years where something new happens. Like, for instance, right now, if you think about open source communities and you think about how companies are so deeply engaged with open source communities, the bigger questions that are sort of coming up right now are, well, what's happening to these communities when volunteers are no longer the biggest part of these communities? I mean, and actually it's company employees and a mix of company employees, and this is changing the nature of communities. It makes them more sustainable, but at the same time, it raises so many other issues as to ideology. Will it stay open source? What does open source mean? So there's, for me at least, there's so many things I still want to work on in open source that I sort of continued in the field. I look at the Linux kernel, which is a part of the GNU operating system, basically, right? So the Linux kernel mailing list is where I found most of my data. This is also often coupled with a lot of interviews that I've done with very key software developers within the Linux project. They've gotten to know me over the years, and I'm not sure if they're fond of me. I don't think I'd go that far, but it's interesting that they do give me time and give me interviews. And this includes people like Linus Torvalds and other key people in the project. And if any of you are familiar with open source, you've probably heard the name Linus Torvalds. So there's lots of, this material doesn't just come from the mailing list itself, but it also comes from interviews and other sources as well. So looking at this community and trying to figure out, okay, well, they use algorithms. They're always building algorithms. They use version control software to resolve most of their issues for coordination. So version control software sits at the heart of most communities, organizes, manages their work, stops code being overwritten by different developers. So it's a fantastic piece of software, and it works and it's efficient. So why do software developers then need to constantly not just tweak version control software, but also build other algorithms? And I'm not talking about building Linux code, I'm talking about algorithms that they have to write in order to be able to write Linux code. So this is not about Linux code itself. It's about being able to actually write any code as a community. So these are algorithms that software developers write in order to expedite, improve their actual coordination and management of work over time. And we know that in open source and in most other online settings, when you've got distributed forms of work, you need to rely on modularity and parallel development. These are two key pillars of online work. And again, because I can't see your face, I'm not sure just how much to sort of go into modularity or bore the hell out of you about the key elements. So, Panis, any hints as to how much? I mean, I'd be happy to go into great detail or just sort of go through the literature. Is there a requirement? Do you know?
I think it would be great because not everyone would be familiar with this literature. So if you can provide some context, that would be great.
Okay, sure. So, okay, so parallel development first, all right? So when you're working in a distributed setting, you need to be able to work in parallel to other developers, which means working simultaneously, sometimes on the same code, same issues, same problems. But because you're across the world and you're not talking to each other directly, and you don't know that somebody else might be working on the same code, you've got to be able to have parallel branches, parallel versions of the same code in order to be able to do that. And this is in a very basic, simple level. We can get more technical. And sorry, I'm sure there are computer scientists among you that are cringing at my interpretation. And then there are people, I'm hoping, from sociology and otherwise who might think, okay, that kind of makes sense. So I'm sorry, I won't be able to hit the right spot for all of you, but I'm just trying to hit the most basic, and then we can deepen our ideas from there onwards. Modularity is a slightly different issue. So code development in online settings, you've got to fracture the problem that you're going to try and resolve. If you've got a big problem, you want to break it down into smaller sub problems so that lots of different people can work on it simultaneously, firstly, but also the problem's got to be small and manageable enough so that people can resolve it. So if the problem were too complex, you'd find that most people would especially if you're thinking about volunteers, they're working on a problem that they don't have to work on, unless they were doing it to gain reputation or they really got some real buzz out of fixing the problem. Most people would look at the problem and say, oh, that's going to be too much work. That's more than 10 minutes of work. And they'll just disappear and the problem would never get resolved. So modularity has a key element to play in distributed work, that it's about breaking down the problem into smaller sub problems. This comes up a lot more for other forms of open innovation. For those of you who are interested in crowdsourcing, are probably familiar with the same idea as to how do you actually design the problem space itself. But you've also got to have modularity of code itself as well, so that you build small solutions. You build solutions to small problems, but each solution must also be it must contain everything it needs within itself. In very simple terms, it should be able to solve that one problem and not affect other modules too much, so that we're loosely coupled with other solutions, so that I can take out this one module out of a system and it actually won't have much of an impact on the rest of the modules. This way, lots of people can build a very large piece of complex code quickly. I'm hoping that makes enough sense, right? So just in a very basic setting, and again, apologies to the computer scientists in the room, right? So open source relies on modularity and the ability to work in parallel. If you're interested in trying to see how this kind of simple work is built up over time in different layers, which are super positioned on top of each other, then I really point you strongly in the direction of this beautiful paper by Howison and Crouston on super positioning, as they call it, by how complex problems are actually put off for much later. So it's deferred and you build up slowly, layer upon layer over time, where simple problems build an entire set of functionality, and then the next is very lovely work. And it was very key for our work as well, because we kept thinking, well, okay, if we've got all of these problems and all of these solutions, then why do these developers in Linux especially keep building new algorithms to resolve issues which supposedly have already been resolved by modularity and parallel development? Well, then other literature also tells us that you can have over-modularized code as well. It's so broken down and it's so fractured that actually it becomes a different issue altogether. Or under-modularity, which according to Narduzzo and Rossi gives rise to unorthodox modularity, as they call it, that there isn't enough modularity. So there are a number of issues. You can have over-modularized codes, under-modularized code, you have superpositioning. So all of these things are working, and yet there are still pressing issues about online collaborative innovation that require new workarounds or constant change in workarounds that are necessary, at least in Linux. And I say at least in Linux because for those of you who come from more of perhaps a positivist or quantitative background, you might argue, well, you're looking at Linux, it is one special case. How far can you generalize? As far as I'm concerned, we can't generalize from any case, but I'm not going to get into any of those arguments with the quant people in this room. What I will say is that this is an in-depth study of Linux. And so what I'm saying holds true for Linux, but I think it translates to multiple other settings as well, right? Then we looked at Baldwin and Clark's work. I mean, if you don't go to Carlos Baldwin's work for modularity, then you really haven't studied modularity at all, have you? So for those of you, sorry, especially PhD students, if you are interested, please do look at her very, very amazing work. And her argument is that actually modularity in a system, it requires, it builds tolerance to uncertainty in a system. But what's really good is that this kind of flexibility and tolerance to uncertainty doesn't actually, it's useful within modules, but it doesn't actually allow a system to have a cross-module flexibility and tolerance for uncertainty. Again, this sort of issues sort of were triggering in my mind as to why, okay, now we understand why perhaps in Linux, we saw a number of different algorithms that were being built and redesigned as what we called workarounds initially to sort of resolve issues of online collaborative work, which should have been resolved, we were hoping, by just simple modularity and parallel development. I'm just gonna, sorry. So it is about algorithms then. I mean, for us, it really was. It wasn't just automatic, oh, let's just focus on algorithms. We're so excited by them. Actually, for a long time, I kept thinking this wonderful craze about studying algorithms right now is all about studying artificial intelligence, and people are getting so excited by that, and especially people in management, not so much in IS and computer science, but definitely in management, people who probably weren't so acquainted with algorithms and find them this intriguing little character that we need to unpack a lot further. I mean, I think for people like us in IS, algorithms are something that we've had around us all the time. We often take for granted, and are those sort of quiet actors where we talk about functionality and systems too often, and rather than algorithms. So I was a little resistant about writing a paper on algorithms at first, thinking, isn't this just jumping on this beautiful new bandwagon? It's really sexy right now. Let's do this. But then when I looked at Linux, and please bear with me on this, and you can crucify me later in questions about this as well, but I mean this quite sincerely. I came in quite cynical into my data thinking, can algorithms really do anything? And then when I looked at these three algorithms, especially that we looked at in this, and there were many others that we could have chosen as well, but we only focused on these three algorithms, which I'll tell you about in a minute. We noticed that actually over time, how these algorithms were constantly tweaked, and they were about resolving issues that modularity alone wasn't able to fix, or parallel development and a combination. So it wasn't just about, oh, algorithms are sexy right now. It was about algorithms actually are designed, and this is not a paper on AI. This has nothing to do with intelligent algorithms in the way that any of you in the audience, and I know Panis is, but I'm sure there are others in the room as well, who are working on artificial intelligence. This paper has absolutely nothing to do with artificial intelligence. And yet these algorithms are sophisticated, elegant solutions to very complex problems. So we looked and studied how algorithms were being designed, and these multiple algorithms were being run simultaneously to resolve issues. What was then even more interesting from the data was that, of course, these algorithms don't work in isolation. They work with other algorithms, but they also work with other human actors. These software developers not only build them, because they are the same people who build these algorithms that use them, which is a very different setting from, let's say, most work on platform, where designers are separate and users are completely different characters and actors in the whole system altogether. So it was about algorithms and their interactions, because they're not predictable. So algorithms, if they are, and I'm just sorry, I'm going to come back to my research question, but I want to, sorry, I should have put this, I just want to come to my definition of an algorithm, and then I'll go back to the research question, I promise. So, how do we define algorithm? We first went to, and I don't know how to say this person's name. So it's the Moskovakis, I think, and Panos will probably correct me
Yes, that's right.
on the pronunciation here. So very technical definition. But then we looked at Lynch's work and realized actually we don't want a purely technical definition, because, well, I believe in socio-technical ideas, and most systems are socio-technical systems. They're not just beautiful, elegant systems designed for a perfect world, which is just used by other technical systems. People engage with systems. So we sort of used two different, at least, scholars in their work to redefine algorithms as a set of instructions that can be computed in a particular order. So they do have clear instructions. And these instructions are supposed to achieve a goal, and that's a given. And so that's very technical instructions that achieve a goal. Straightforward, those instructions are linear often, and they are followed in a very clear way. And if something goes wrong, the algorithm stops, and so on. However, we then say, but this includes the possibility of unforeseen outcomes arising from the unfolding of any set of algorithmic instructions in parallel distributed work. Meaning, when you have multiple algorithms working simultaneously, they're not just working in isolation. One algorithm's instructions is often dependent on other algorithms' instructions as well. And this can create different kinds of interactions that lead to unpredictable results. We have only to look at our own everyday use of any computer to realize that actually happens. Oh, how am I going to go? Oh, yeah, that happens all the time. So algorithms aren't as predictable as we hope or believe they are to be. And I think management scholars tend to think sometimes that they are a little too much. And I think information systems people have a little bit more awareness of this. Algorithms can freeze, they can stall midway through execution, some break down, and often they produce incorrect data. So why would that happen if it's all about just following simple instructions? This leads us to our research question: is how do algorithmic interactions, and when we talk about algorithmic interactions, these are interactions with other humans and with other algorithms as well, shape open source work? So, okay, so they're shaping open source work. So developers are using algorithms to help them. So their algorithms are an extension of a human's ability to actually be able to function. This brings in the key idea, or at least for us was very key, at least first, augmentation. And augmentation, as we know, if you go back to Engelbart's work in 1962, is an extension, an amplification of the capacities of human users, right? So augmentation, as we know, is always about a human's work, or a human developer or otherwise being able to do yet more with the help of some sort of technology, and in our case, an algorithm. So it's not about automation, which also we know from literature is about replacing human work. So you kind of cut out the human and rely purely as if we've got this wonderful clinical world where algorithms just work on their own. We have there are some settings that are like that. And I'm not saying that there aren't, but those settings aren't what we often come into contact with. And at least in my scenario of the Linux kernel development, that actually didn't happen at all. Humans were involved at every step of the way almost. there's a lot of literature that sort of argues, and this is probably a little bit more management, that says, we need more augmentation. The human shouldn't be ignored. The way forward for the future of work, and for those scholars amongst you in the room who are looking at the future of work, which is, I think, a very interesting area to look at these days. How is that changing the workplace of the future? Are we going to work with technology and let it help us shape each other, or is it about just being replaced by this technology? And the management scholars say, no, don't ignore the human, because what are we going to do without work? And AI is so intelligent at some level that we can't reskill fast enough. So there are all these kind of scary stories going around that we will be made defunct as humans and our value will be lost. Then this really nice piece by Reich and Krukowski in AMR on automation and augmentation actually being sequential processes. That they argue, well, actually, you often have both, not simultaneously. So we as humans in an office place, for instance, will augment our work. And then over time, we'll begin to understand our technology better and realize which parts of our work, now that we understand the technology better, can be further automated. So we automate more of it. And then you have a moment where greater automation happens. So they talk about sequential augmentation and automation. Again, this literature was quite interesting because we kept looking at our case, in the Linux case, thinking, yeah, but that's not happening. We don't see the sequence. We see this happening most often side by side. These developers, is there something specific about the Linux case? Is it when you are the developer and the user simultaneously? This sort of sequence doesn't happen. So these are questions that started to sort of arise for us. And then one of the reviewers very kindly said, well, really, do you think you know enough about automation? Perhaps you should go look up Bainbridge's work, who talks about the paradox of automation, which kind of threw us off base a little bit initially, thinking, okay, so she argues that there's a paradox of automation, that in any setting where you think you're working with purely automated settings, actually, you've always got what she calls human operators. People who are fixing the algorithms, making sure they work, maintaining the work. And these are people nobody knows about, nobody gives them any value. These are the lowly, invisible scut workers, basically, of software development. But the argument is that automation is never pure automation, thus the paradox of automation, right? So we have to think, oh God, okay, so humans are never completely ignored. So where are we then in open source? Are these software developers scut workers? And so questions began to arise. I'm just looking at time, and I realize that, as I said to Panis earlier, I do tend to go on for a while. So I'm going to go into methods lightly and not too much detail, not because they aren't important. God knows we know how key they are and how reviewers tend to kill us on them. But my research setting is the Linux kernel community. The data collection was about okay, so I looked at the Linux kernel mailing list, which is the LKML on my slide. And then we also looked at GitHub. Why do we look up GitHub? Because of the particular algorithms that I was focused on. The LKML was less vocal about that particular, because it was part of Git itself. That's why GitHub was more had more conversations going on it. The time period of email exchange that I focused on was from 1999 to 2005 on the Linux kernel mailing lists, and then 2005 to 2018 for GitHub itself. We also focus very much on three key algorithms that I collect. In the sense, I did the data collection, but the paper, of course, is from both of us. 410 specific emails that I collected on the topic of BitKeeper, which is a particular version control software, and then 76 messages on Git, related to Git. I did 7 interviews of influential software developers that were either part of both BK and Git, or just Git, or yes, only Git as well. And then there was archival sources and technical documentation and so on. This is grounded analysis. So again, happy to answer all questions about this later on, especially with the PhD students. How do you build theory from this, and what are the kind of issues that arise? We found 3 distinct algorithms that we wanted to focus on. There were many others. We only chose 3. Why? And I'll tell you that in a minute. And we had different levels of coding, and so forth. So why do we look at these 3 algorithms? And I think this will trigger something in you. BitKeeper, a particular version control software. So that's the BK. Sorry for the short form. Just trying not to make my slides too cluttered. So BitKeeper's auto merge was the first algorithm. This is a very interesting algorithm. It merges code patches automatically, meaning if you so if one individual, so all of you in this cohort right now online, all tried to fix the same problem for Linux code simultaneously and sent your solutions in around the same time, BK's auto merge would flag up the second developer, but instead of flagging it up to the second developer to say, which would have been usual for most version control software to say to the second developer, could you please decide that there are 2 solutions to the same problem, which one is a better solution? Instead of asking the human developer, BK's auto merge was designed to make these decisions for itself. Right now, this was excellent, beautiful piece of code, beautiful lines of instruction that had to struggle with creativity of software developers while automating work. So think about it. These are software developers of an expert level. We're not talking about novices. And when they send in code solutions, it's very hard to design an algorithm that is able to match different criteria and say, this is superior code. So BK's auto merge is a very sophisticated algorithm. The software developers in the Linux community didn't like it very much. Surprise, surprise, right? BK's time sync. So this is when patches are sent into for acceptance into the larger code. BK's time sync is an algorithm that had to be written to coordinate work. What did it do? It gave each individual patch that was submitted a specific timestamp. This is not about chronological time, because as you know, people are coming in from different parts of the world. There are multiple servers being used simultaneously. So this is about one unique timestamp that this algorithm would give to every piece of code. And why is that important? Because you can then check code backwards and forwards in time. And this becomes more important when you're looking at multiple versions. If one area of code suddenly breaks down and isn't working, software developers can decide, well, actually, why don't we just kill that version for now and work with another one? And then they could move backwards in time as well. So it's a very important piece of functionality that modularity of code doesn't take into account, and parallel development doesn't do justice to either, though of course it relies on parallel development as well. And then you've got Git hooks. So this is why we had to go to GitHub. Git hooks are so in software development, you have continuous integration. What that means at a very basic level is that as lots and lots of hundreds and thousands of developers are writing new patches of code and trying to submit them, it can over time build up issues for testing. So the idea of Git hooks is to do continuous testing so you can integrate code quickly. Right? So it's about not testing very, very, very large chunks of code per developer, but it's about, okay, I'm about to submit this. Let me just test it on this little space or in this little version. If it holds true, then it's more likely not to break the system down. So Git hooks are, again, very important pieces of, very important algorithms that actually allow for efficient and quick distributed development to happen. All right, so these 3 algorithms, we focused on them over time, all right? We focused on their different interactions, as I said, between developers and algorithms with other algorithms. Any questions, sorry, at this point? Anyone that I was looking particularly confused or worried or... or bored even. And then please let me know, because I'm happy to go faster, because that can be, well, that's the way to kill any conversation, right? Boredom. Are we okay? All right, thanks. Okay, so on these slides, we could go into different quotations, and I'd be very happy to go into detailed quotations. I often think that just reading off quotations to you is boring in an audience. So I'm going to talk about the 3 different processes that Emma and I found through our data analysis steps. And how did these different processes emerge? So I was looking, I would look at the data, I would do the analysis, then I would go back to Emma. So this is especially for those of you who are doing grounded theory and are a PhD student. How do you do this kind of grounded theory where you need a second person to really hammer your codes and tell you this is, are you sure this is holding true? Isn't this just a repetition of your code? You've got your supervisors for that. So, but it is an important part of testing the strength of your coding process. So I found a number of different kinds of interactions. And when I found the same sort of interaction arise over and over again in the history of every algorithm, I started giving each of these different types of interactions, a particular name. Then I would go back to Emma and I'd say, oh my God, I found, categorizing, calibrating, invoking, and defective, and 7 other interactions that I thought were really useful. And then when she and I would have a discussion, we ended up with, which were actually, I'm sorry, I had to sort of just to break it down on the screen. I put this as 3 different kinds of interactions, but it is categorizing and calibrating was 2 separate ones. So there were 4 different kinds of interactions that we found that were really influential. So we found this. Then we found 4 deactivating, simulating, seeking, reversing, and then forceful, extending, and reconnecting. And this went on, believe it or not, forever. I mean, we had so many different kinds of interaction that Emma nearly went crazy. And so we then had to sit together, and this was the next stage of coding. How does it make sense to understand these different kinds of interactions? When do we see these kinds of particular interactions coalesce together over time? Over and over again. And so then what I realized was that categorizing, calibrating, invoking, and defective happened most often when we found that there were problems related to parallel development. So then the broader abstraction here of our grounded theory, we named as managing parallel development. Of course, the name got tweaked over time. Deactivating, simulating, seeking, and reversing interactions, we realized actually these came about often together. And again, as I said, this was about modularity issues, resolving modularity, and the same for the last. So you get the gist of it, right? So we went into axial stage of coding where we were looking for relationships and relationships over time. Just to give you an idea from the time sync, and I'm only going to read 1 quotation, I promise you, and then we'll move on, and I'll take you to the actual model itself. So I kind of like this quotation. The developers say, BitKeeper's owner and creator says, our time sync features, this is the time sync algorithm, one algorithm, ensures that all files in a repository always obey the same timeline. This guarantees total reproducibility and prevents broken builds or indeterminate states. All the files and components are always consistent. If one is rolled back to how it looked 3 weeks ago, all the others are rolled back as well. This eliminates broken builds due to out of sync libraries and configurations, right? So what they were doing was giving each patch a particular time stamp, so categorize, giving it a stamp. That was a category. And then they calibrated because they could actually reorganize these different kinds of patches that were coming in and how they were interacting. And then we had invoking, and then when things didn't work out, we had defective, which is when we realized parallel development was actually working with modularity issues. And here we had deactivating interactions that were triggered because of some defective interaction that had happened in the overall aim of fixing a parallel development issue. Sometimes algorithms were created to simulate an interaction. They were pretending, and they had to, because one code was calling on another where the path had been renamed and it couldn't find the right algorithm. And so they had to pretend that they had found it. And the seeking interactions, reversing interactions, and so on. So we found a number of different kinds of interactions multiple times over time. This is our model, which went through multiple iterations. Let me just put it this way, right? So you see the three key processes that we built from our coding. At the top, you have processor parallel development. The bottom is organizing modularity challenges. And on the far right, process of supervising open source. And you've got the different kinds of interactions that are part of each of them under them. For each interaction to happen, sorry, I didn't go into this in such detail before. For any interaction, for me to figure out what is an interaction in my code, which is really important, right? How do I know this is an interaction? I looked for a task being performed, an interactional context, meaning what is happening here, what is being resolved, and the design of the algorithm. It was coming together, the confluence of these three characteristics that actually I sort of realized this is what I'm going to call an interaction. And this is important, especially for PhD students who are at this process of time trying to figure out, any issue. What do I see as coordination? What do I see as control? You're going to have to break it down into granular terminology so that you can actually convince your examiners or paper, hopefully publications and your reviewers that yes, you were able to find this because you were looking for something specific, because control, for instance, or coordination, these are big terms. What do you actually mean by them? And so we had to explain to our reviewers, what do we mean when we said we found an interaction? So multiple interactions are triggered either by a human or by an algorithm or both. We looked for these interactions. We noticed that these different kinds of interactions were triggered. And here we found that actually in some cases, algorithms were being used to help the developer resolve a problem. But over time, what we found was the developers, the key aim of most of these Linux kernel developers was not that we should always have to constantly tweak our algorithms and change them. It was like, oh God, this is a problem and a pain sometimes. Let's try and automate our work as much as possible. So in a lot of platform work, you realize and you find that people are saying automated work it happens all the time, but it's a problem because it means managers are having less control, and users and laborers on these platforms are really at a disadvantage. What we found in the Linux case is they want automation. My God, automation resolves so many issues. In every case other than the auto merge. And that's a very specific case. And we can keep that for a discussion another time because we probably, looking at the time, I think I'll just keep moving. So I promise you now, especially to Tahir and Panis, I'm coming to I'm concluding now, right? So contribution. Looked at the study, found, okay, modularity is an issue because it doesn't resolve all issues. Parallel development doesn't either. So how do we understand it? Well, looking first at the augmentation literature, prior literature has actually talked about, how do we actually augment human work? So it's not, Eben talks about invisibility of human work. We also know that from Bainbridge's work of paradox of automation, that she too talks about operators of algorithms and systems that are invisible and who do menial work. So there is literature by Eben, Igbia and Bainbridge that those of you who are interested can take a look at as to how workers in software development fields can be made to do invisible work, menial work, on what we might call scut work, taken from, of course, the words that other people use often in hospital settings in org science. Ruthane Husing, I'm sorry, I don't know how to say her work is amazing, but I can't say her name properly. So looking at that sort of work, what is the equivalent of scut work in software development? Well, people would argue actually writing software development code that does invisible work. And yet we found actually firstly, our process model showed that algorithms don't just augment work and don't just automate work. They do both. They don't do it in a sequence. It's not one after the other. It's done simultaneously. So it's a bi-directional relationship. And in all honesty, these are not, these developers do anything but invisible work. These are high-profile software developers that shout very loudly when they achieve a solution and are given kudos for it. They gain reputation. And as we know in open source development, this is how they gain decision-making authority in open source communities, because there's no clear you will be the manager of something. You gain managerial positions through authority, which is again gained indirectly through the reputation of your amazing code contributions. So there is invisible work, of course, in open source, but this isn't it. So if you're looking for invisible work, writing these sorts of algorithms that help alleviate issues with modularity and parallel development, this is not invisible work at all. And then looking at modularity and parallel development, we sort of build on these ideas of Howison and Crouston. So this is more an idea of not contradicting what they do, but complementing what they do, but also taking the call up by Narduso and Rossi and all of these other amazing scholars who said, oh, well then, you know, if there are issues of over modularity and under modularity, well, then how do these open source developers actually still manage to write really amazing code? Well, our software development experiment here, not experiment, sorry, wrong word, very qualitative study actually shows us that algorithms are built to fix these issues. They remedy these lingering concerns of parallel development and modularity. And open source developers are all about building algorithmic workarounds over time that resolve these issues. And this is constant and ongoing. Thank you very much. And I'm happy to take questions. I think I almost kept to time. I did. Surprisingly.
Yeah. That's great. Well, I mean, I'm not surprised with all the details. That's exactly what I expected. Your work is also always very detailed. And for those that are not familiar with this type of qualitative work, you can really get lost in the same way that you get lost with big data analysis, I guess. But it's interesting, a lot of interesting questions and themes emerge from your work. And obviously, there's a lot of interest nowadays, as you said, in human-machine augmentation. So this fits right into it. Of course, with the spin of open source software development. We do have a few people in the audience that are have computer science backgrounds. So
I knew it. I know it. Kill me now. Okay.
So yeah, the floor is open for questions. If anyone wants to ask anything, otherwise. I have a couple, but
as a good chair always does, these are backup questions, so help him out here.
Yeah.
Either I bored you completely, which is why you don't have questions, or it was so wonderful that every question was answered. And I really don't think it was the latter. So
yeah, and maybe move the slides back to the model. Maybe that's
sure. Oh,
that's a way to kickstart the discussion.
Tahir, sorry, yeah.
So
sorry.
yeah,
kind of sorry. I just looked at his name, but I'll let you chair. I'm not sure how you guys.
No, I just wanted to some clarification. I think I can break the ice here. So thank you so much. This topic is absolutely new to me, so it was really interesting to know so much in depth. So I just wanted to learn about the challenges that you identified. Were they any different than in this space identified, like you from the literature? Or in parallel working on this modularity issues, how did you feel like in your data set for Linux? Were there any specific that were only relevant to Linux platform, or do you think it's more generalized ones?
The thing is that looking at, of course, as we always do our literature review and reading other people's amazing scholarship, my work has been on Linux for a very, very long time. Absolutely. Have I looked at other open source development projects? Yes, absolutely. Lots in the public sector and other, and in fact, more recently on AI projects, as we know, a lot of the code is written by open source developers in these projects. And we have seen similar issues, but just going back to the literature issue more, the literature that we relied on in order to build and consolidate our sort of framing, as we put it, especially for the PhD students in this audience, they weren't looking at Linux, and yet they were the ones raising these issues, talking about modularity and talking about it in specific ways. So that's why when I started the talk, I said that I do think that what we found is how problems are resolved through the creation of algorithmic workarounds and open source is about open source, is not just true for Linux, that this actually translates to other settings as well. That's how I would understand it.
Thank you. Thank you, Maha.
Anyone else?
Anybody
Can
who
I ask a question?
Oh yeah,
Yeah,
sorry.
Olga, please.
Yeah, thank you, Maha. This is very interesting talk. And open source is not my area, and I don't know much about it. And I'm not from data science background. My background is in economics and business and management. I wanted to ask a question about your research question. So you phrase it, how do algorithmic interactions shape open source work? Yes. And it's quite a broad question. Yeah. When I started my PhD, I had a lot of comments about my question was too broad. And do you think you answer this question with this research, or there are still opportunities to explore more? Or did you break down your open question, this broad question, into sub-questions? What was your approach? Yeah. And how do you actually, I understand there are multiple interactions happen during the process, but what does shape the open work? Open source work.
Olga, thank you very much. It really is an excellent question. And as you probably understand from trying to publish, which is a very different thing than, yeah, or even the beginning of your PhD where you get hammered. We get hammered all the way through, right? I mean, it's not just the PhD process. In fact, that's just the beginning. They're warming you up usually in the PhD. So how do we get to this question? If I told you that this question went through as more revisions than probably the paper did itself, which is a normal reaction. So we had in the first version of the submission, we had a very specific question with at least, as far as I remember, sorry, this was a number of years ago now. So we had at least 3 sub-questions that we were looking at in a very focused way, which all together helped to build up the answer to this big question, which didn't look like the one you saw right now on the screen, right? So that was already, that question was more specific than the one that you see at the moment. Over time, reviewers pushed us in multiple, I mean, this is the hardest part, I think, on the review on this paper. You can get tough reviews, but they're all aligned. So it means you have to do a lot of work, but all the reviewers tend to agree. So you know you're going to be rewriting the manuscript, but you're writing one manuscript, not 3 different ones to please different people. In this paper, to be honest, we were writing 3 different ones every single time, which is why it was so schizophrenic, the process of writing it, but what I produced at some stages, even I thought, oh my God, what a pile of absolute rubbish, right? Because it was trying to help and make sure everybody was happy. So our research question, sorry, coming back to your question, our research question went through a number of iterations until we finally came to this point. So in this question, I'm actually very comfortable with most words other than what you pointed out. So I like the algorithmic interactions. We're very specific in the paper as to what we mean by it. We define it, we're clear. We say, you know, we build up in the introduction. And this again is for more juniors, not yourself, but the more junior in the audience who might be looking at how do you build up the introduction? How do you frame it? We talk very clearly about what we mean about open source. We're looking at modularity and parallel development. So we're very clear as to which literature we're going to contribute to. But the word shape, and you're absolutely right to sort of hook onto that one and say, come on, that, yeah, you're being very kind, but what you're really saying is this is a big word and it could mean anything. We went through a number of different words. This is the one word the reviewers didn't kill us on. Well, or maybe they ignored it to the point where they didn't care anymore. Really hope none of the reviewers are in the room here, okay? There's always a worry, right? So I don't know who the reviewers are, still don't know, and never will, hopefully. But so we ended up with the word shape because it meant that it's about nudging, but we're not saying this is a causal relationship. And that's very true for qualitative work. We make causal, I mean, theory is about causality, of course, but we in qualitative work, as we know very clearly, we always say, this is one explanation. So when we use the word shape, we are being very open-minded as to the idea that this is one form of nudging. There are many other questions that could possibly sort of dictate what happens in a community or nudge a community into doing things. And as I also mentioned, there were so many other algorithms that we could have looked at, but we focused on these three because they spoke to the literature that I was reading. So, you read, you look at your data and you're like, oh my God, I found a match. So, I mean, am I blind to other algorithms because of the literature I'm reading? Absolutely. I mean, but how do we then otherwise produce anything? I mean, it's a process of reading and going back to data and trying to consolidate one clear, hopefully almost clear research question that responds to something. So have I answered the question for all time on open source? No, and that was never my ambition, or even because, as I told you, I'm passionate about open source. I want to keep going. So there are other algorithms that I'm now exploring for other papers as well with very different issues. It's not about modularity or parallel development, but do they also shape open source work in some way? Yes. So totally take your point, Olga. Very, very good point. Thank you for the question. I appreciate it.
Thank you very much for your response. I just have a similar situation. My question is quite broad: how data visualizations support business decision making. Okay. So that word for me, support, covers quite a lot. But how specifically it supports, I will know.
How did you come to the word support? I mean, did it come from reviewers, or because the thing is, we often use words in our research question. This again is for the PhD students, not for you, but more for the PhDs who often think they can use any word lightly, but actually we often build our research question through theoretical words, right? So how did you find the word support? Was it coming, I mean, can you sort of justify it through the...
It came with a business problem, with how it was formulated to me.
Yeah, that's interesting.
Not only just support with confidence. So decision makers can make their decisions with confidence.
But isn't that really key? Because what does literature talk about support with confidence? Well, I mean, isn't that justification for the use of your word? It's not just a layman's use of the word support. You're actually building it on established literature.
Yes and no. Yes, I'm exploring literature on confidence as well in decision making.
That might help you. I'm
trying to link it to data visualization, yes.
Because we looked at the word shape from more very old literature now, and I'm sure many of you probably heard it and have ignored it since. But the shaping of technology, social construction of technology, there the word shape actually has a particular understanding and meaning in socio-technical work.
I'll have a look at this literature on the word support or use of support in information systems literature.
Or even if it's other literature, information systems, as you know, we're quite open-minded. I found that in most MISQ and ISR, but probably other journals as well, whichever one you're aiming for. As long as the overall aim is to contribute to IS scholarship, it doesn't matter where you draw certain parts of your literature from. So, support, I think you said support with confidence. If that's a phrase that has a body of literature behind it, but it doesn't come from IS, nobody's going to argue against that.
Okay. Thank you so much. Thanks.
Thank you for the question. Pedro.
Oh, Maha, sorry I was a bit late because I just came from a meeting with a PhD student, so I may have missed a bit of the beginning of your talk.
Then your question should be easy, hopefully.
for your presentation. And I have a question around the stability of the environment, the community that you research, because open source is a phenomenon in a group of let's say activities that is quite, I would say, established for a long period. So there is open source research communities, and these have been crystallizing for quite a while now. So the reason I'm asking you about the stability of the community that you were investigating and its impact in the model development, because I'm trying to understand how data wrangling works, the impact of people's interaction with in the early stages of data science. So this is an area that is just beginning. People don't know how wranglers wrangle, how they develop the scripts. It's hard to say what modularity means. There isn't a clear-cut way of how you supervise the process or how you would organize groups of teams working at these stages. So would you, give any advice on how you would tackle something that is in a much earlier stage of even, the way the phenomena you would organize or think about the actors or the activities? Thank you.
No, thank you for the really, actually, that's a very interesting question. You're right to point out that this is a community that has been, I think, ongoing for 31 years now. I mean, I'm not, sorry, yeah, I think it is. I think it is 31 years. I can't remember the exact date. So we're not talking about a project that's just started. This is one, it's not the oldest, but it is one of the oldest open source projects. And not only does it have the big name of one of the oldest projects, it is one of the most successful cases. And when they talk about success of an open source community, we're talking about a sustainable open source community, which means, as you pointed out, a large number of developers, high turnover of software developers. So you raised the issue of stability, and I'm not sure what that means, because in open source, there's a stable core development team, but the peripheral developers are in flux. And in fact, that's how change happens. New ideas come in, and you want that to continue. So what you want is stability in the middle core and change on the outskirts, so that things, and so over time, the peripheral developers, as you know, probably from Linus Darlander and other amazing scholarship, that over time, these peripheral developers start to stick to one community, consolidate their reputation, and become core, so that the core team can also have a little bit of turnover as well, because, in the Linux project, people haven't, other than Linus Torvalds and some other, maybe another 100 developers, others have changed over time. And there are 10,000 developers, by the way. At any one point in time, the Linux project has about 10,000 developers, which is, by the way, freakishly large for an open source project. Coming to your question about how do you actually understand how to manage these interactions, how to even build up modularity or parallel development, my argument would be to you that actually in open source, if you look at the older literature in open source, where the stuff is on governance of open source community, health of an open source community, I don't mean the recent stuff, I'm talking about the older stuff. Why? Because what we know even today is that most open source communities die. I mean, so nowadays, because companies, and this was the issue that I did raise early in the presentation, that we're not talking, Linux project does have a lot of company interest now as well, but still the balance between volunteer and employed people from companies working on this community is still fairly balanced. This is not true for all other projects. So if you're going to start off a new open source project, a number of years ago, the 99% chances were this project's going to fail. I mean, you didn't even get to the point of worrying about, which version control software should I use? Because you wouldn't even need one, right? So what you raise is an important dilemma for people only once you gain a certain size. So if you want to establish yourself, how do you actually build a promiscuous community, meaning that allows for, it's kind of like the same kind of questions that people are facing, and Panis may be able to address this, you know, in a very interesting way from his work on platforms. You know, platforms were, when you start off a platform, it's all about growth, and then it's about consolidation. And you can take a look at Wikipedia both as a platform, but also as an open source understanding of how we build knowledge. It kind of actually keeps both of those ideas together. It was about building number of people adding code, and now they're about having a governance structure in it, so they've got legitimacy, editorial roles, and so on, so that they can consolidate. But growth has slowed down substantially, right?
Yeah.
So I don't think your question will become such a big issue for the community, whichever one you're studying or which one you're helping. I think until it grows to a certain size, what that size is, I don't know.
Yeah.
Does that help?
Yeah. The problem is even the terminology, like in open source, the processes and the way you would expect the community to coalesce or organize the structures of development, you know, the way the problem solving works is there's quite let's say a body of knowledge to help you to think about how you would approach the problem. The problem with data science and data wrangling in particular is even that the terminology itself is not widely acknowledged. So there is a fundamental problem there in departing from concepts. And the idea of, as you said, modularity and the way you organize development, it's also not clear-cut, because unlike software engineering for programming that has an established discipline and ways of problem solving and addressing issues, in data science, it's, you know, we're in such an early stage, especially in data wrangling, that there is no established discipline there, okay? So sometimes when I interview people that are very expert data wranglers, it's hard to understand how they develop something. Do they start first with the data, or do they